experimenting again. This time I've lowered the height of the camera, the camcorder, because I'm on the lower part of the board and the camera is now very close. Also, I've switched off the light here. It's very bright and it hurt my eyes before. So, and since this is, what's the time? It's 3 p.m. So hopefully there's plenty of daylight to make this come out quite well. Anyway, just experimenting again. Alright, so we're talking about without resorting to the full force of Dirac's graduate level equation, the Dirac equation, which is relativistic. And to understand that, you need to have done special relativity, have a good dose of quantum mechanics, so not ready yet. The fourth course, this is the second, that I'll be teaching. The third will be on theory of computation, computer theory type course, quite a long one, about 400 pages. But the fourth one will be on special relativity, and then once you've got that under your belt, and this quantum mechanics course, and also first year masters M1 level quantum mechanics course, then I think you're ready to do the Dirac equation. So a whole level up, level and a half up from where we are right now. Anyway, but without using the big guns of Dirac's equation, we can still do something. So here's a suggestion. We're trying now to find a Schrödinger equation that deals not only with the position, the position vector r of the particle you're talking about, let's say, but also the spin. So, and the suggestion is let your wave function now be a two-component wave function here. So, and what's the motivation behind that? Well, it's similar to the spin vector, right, which is a 2x1 matrix, a column vector, in other words. So this component, this part of this two-part wave function, that would be relevant to the spin up. Remember, when you're talking about spin, there are only two eigenfunctions. It's just spin up or spin down. That's it. So it makes a certain amount of sense to talk about the wave function of a spin particle as in two components like this. Now again, that's just a hypothesis, right? Lots of what if type suggestions, hypotheses in quantum mechanics. But it seems reasonable, given that when you're talking about spin, the eigenfunctions are column vectors. Right? So this would be, in this form, it's relevant to spin, but we can have, with our two components, we can have each component talking about, as a function of r as well. So in a sense, this component here is the component, the wave function relevant to the spin up and the position, and this one would be correspondingly for the spin down and the position. So if that's your new wave function that's relevant to both position and spin, then presumably the Schrödinger equation would look something like this. Right? So Schrödinger equation is just the Hamiltonian as usual, h hat, and a wave function, and the dBdt wave function. All right? But in this case now, the Hamiltonian's a bit different. It will include terms remember the Hamiltonian, classical mechanics, Hamiltonian is really just the total energy, like the kinetic energy and plus the potential energy. And the Hamiltonian quantum mechanics is just the same, except those physical quantities get rewritten as operators. Okay? Now, presumably when we're talking about spin, in the Hamiltonian will be terms that are relevant to spin. There'll be potential energy terms with that depend on the spin. I'll talk about that a bit later in future sessions. So your Hamiltonian can have spin-dependent terms. Okay, so that's the way you think the Schrödinger equation would probably look if you have this two-component wave function that's analogous to the spin eigenvectors, right? Okay, well, if that's your wave function, how do you interpret normalizing it? Right? You always have to normalize your wave functions so that your C1 squared, C2 squared, whatever, so that they come out as probabilities that make sense. So that the sum of all the probabilities has to be 1. Right? You want the sum to be more than 1. It makes no sense in terms of Born, B-O-R-N, Born's probabilistic interpretation. Right? So you need to define how to normalize. So, well, here's a fairly obvious suggestion, right? Well, before we just without the plus, when we had a one component wave function, we normalized by having psi star psi. Well, I don't know if the order is important or not. Anyway, this seems a reasonable suggestion. Now we have two components. We'll add the two components squared in effect. They're complex numbers, so take a conjugate with itself. Like z. Let z be a random complex number. Then z star times z will always be a real. Right? That just comes out of the math. So similarly here, you want it to be a real number, and let's define, multiply these by some factor, normalization factor, so that you get 1. All right. So what are these two things? Well, the square of them, if you square this, that gets interpreted then a la Born, by analogy, close analogy. So the square of this psi1, the first component, is interpreted to be then the probability of measuring that you get for the measurement the spin up value. Right? So you just square that, and that'll give you the probability of getting a spin up result. Okay, and similarly square that would be the probability of getting a spin down result. Okay, and those two probabilities, you square that plus you square that, you get 1. I mean, the result's got to be either up or down. It's one or the other. Right? That's your normalization. Now, if your Hamiltonian now does not have a spin-dependent term, so if your Hamiltonian here, if it is independent of spin, then you don't need these two components. You can just go back to your one component. So if H is spin independent, you don't